Can you hear me? Hello. 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 Okay. Right. We'll start with the problem solving session for week 11 in the digital circuits course code EE115. There are 15 questions and I'll go through all 15 of them. They are from the previous year assignments, I think. And if you have any doubts, you can unmute yourself and ask me. Some of the questions might be repeated this year, this sem also. I'm not sure, I haven't checked for this week. Usually we remove such questions from the problem solving session. Let me check if it's recording. Last week I forgot to record, so I have to re-record and post it again. I haven't posted last week's session. If you are unable to ask your doubts through your speaker, then you can type them in the chat. And don't wait till the session ends to ask your questions. You can ask in whenever you can interrupt me and ask in between. Alright, we'll get into it. How many T states are required to execute move AC instruction? You can type the answer in the chat if you know. Four. Yeah. So, one thing to note here is that the number of T states required can be different for different microprocessors. So you'll have to go and check the datasheet of the microprocessor to know how many T states each instruction will take. But since in this course we are dealing only with 8085 microprocessor, then we can assume that the question is also asking only about 8085 microprocessor. And for 8085, for move instruction you need 4 clock cycles or 4 T states. And timing diagram was done in the class. So in the first cycle, the ALE signal is set high and the address is loaded on to the address bus. Next clock cycle, the read signal is set low, so read bar will become high. So it's an active low, you could say. So whenever you give a low signal to read bar, it will read. And in another clock pulse, the data from the memory will be read by the processor and stored in a temporary register. And then one more clock cycle. Well, we don't exactly know what is happening in the clock cycle, but we could guess that the instruction is being decoded. So 4 clock cycles, that means 4 T states. Okay. Question 2. What happens to the content of the stack pointer after push instruction is executed? The 4 options are firstly, is the stack pointer incremented or is it decremented? That's one thing you have to know. And whether it is incremented or decremented, by how much is it incremented or decremented? Is it incremented by 1 or 2? This was done in class, so if you have read the notes or watched the video lectures, you should know. Okay, by 2, it's I think this is the last slide of the lecture notes. So first, when you want to execute the push B instruction, then push instruction, then you decrement the stack pointer, copy the contents of register B, then decrement it again, copy the contents of register C. So when you do a push operation, you have to uh, copy the contents of the register as a pair. You can't copy the contents of a single register. You can't copy contents of just B. The contents of C will also be pushed onto the stack. Okay. So there are two decrement operations. So the answer is option B. Contents of the stack pointer decremented by 2. Okay. In 8085, which of the following instructions update the program counter? Is it PCHL instruction, only add instructions, only jump and call instructions, or all instructions? What do you think? Don't know. Well, what is a program counter? Okay, a program counter is used to keep track of the address of the instructions. So when you write a program, a you'll write a set of instructions, right? It won't usually you don't want to execute just one instruction. You want to execute a set of instructions in a sequence. So you'll write those instructions and those will be stored in a memory. Say let's say you start storing from this address. Maybe the previous contents are all filled. So at this part of memory, this will have some address. Say this is 10.0.0.0.a. That's it, in hexadecimal. So here one instruction will be stored, and the next instruction will be stored here in the next address. The third instruction will be stored in the next address, and your set of instructions will be stored in a few address locations. So that constitutes your program. So you write the program and then you want the microprocessor to execute that program. What do you do? What does a microprocessor do? Initially, this program counter register will store this address. Where does your program start? So you have to load that onto your program counter. And then once it knows where your program starts, it will fetch the first instruction Okay, and then it will decode it, execute it. Let's say you're loading some data onto the accumulator. That's what it is. Or maybe you're moving some data to the accumulator. Move A comma C. This one, let's say the first question. Let's say that's your first instruction, and then you want to add directly some number to that content. So once it does the first instruction, this program counter, it will increment it by 1. It will go to 000B in hexadecimal, that is this, and then it will fetch the second instruction and execute it, and during that time it will increment it by 1, 000CH. There will be one instruction here, so it will keep track of at what part of your program you are. Okay, so once every instruction is executed, the program counter has to increment by 1. So the program counter content is changed by all these instructions. Okay, PC add, jump, call, all instructions will change your program counter content. Any doubts? Okay. Question 4. If CS is equal to A15, A14, A13 complement. So this is complement, or you could write this. So that's complement is used as the chip select of a 4K RAM in an 8085 system. Then its memory range will be. I'll give you 1 minute. Think about it. There are 15 bits in the address. A0 to A15. Actually, in 8085 they are called here AD0 to AD7 and then A8 to A15. So those are 16 bits actually, not 15, 16 bits. Maybe where was the address part? Yeah, maybe this picture will help you understand better. So some of the bits are used. So these bits. Okay, we can't have it. These. See here, these bits are used as chip selection circuit, and these bits are used to access the actual address. So what this means is that inside this block, right, this memory block, there are actually smaller blocks, let's say, and they each have registers. So these bits A0 to A9 are used to name these smaller blocks, each of the registers in these smaller blocks. So this thing has multiple blocks like this, and each of these has a set of registers. Here maybe you could store 1 byte here, and then each of this address location is given by 10 bits from A0 to A9. The rest of the bits, A15 to A10, are used to select which block inside this memory chip that you want to access. So here, let's say I had maybe some concrete numbers would help. Let's say I was using only the 15th bit to select a chip, okay, and the rest of the bits A4 to A0 were used to select the address within one of these blocks. So you could say that whenever A15 is 0, I will access this block, and whenever A15 is 1, I'll access this block, and within this block A0 to A14 will give you one of the address locations. Did you understand? I can repeat myself if you didn't. You understood this part, right? So some of the bits can be used to access a chip, and the rest of the bits can be used to tell you the address within the selected chip. So similarly, in the above question, we have 3 of the bits are used to access a chip. So they are chip select bits, and the rest are used to give you the address. So in a sense, the address range would be, so wait a bit. Okay. Okay. Uh, that is if you have multiple chips. But here they have given only one memory chip, right? So it's a bit different here. So if you have only one memory chip like this, then they'll use these bits to determine whether this single chip is being accessed, right? So they will use some combinational circuit. In the question in the assignment, they are A15, A14, and A13, and the combinational logic they are using is A15, A14, A13 complement, right? and if this signal goes high, then the memory chip will be selected. If that signal goes low, then the memory chip won't be selected. So for that purpose, we want A15, A14, A13 complement to be equal to 1. When will that happen? Somebody should answer. You don't know? See, these 3 bits will select the chip, and suppose your chip is selected, then what does that mean? It means these 3 should be 110, right? A15, A14, A13 should be 110. Only then the chip will be selected. Suppose A15 is 0, then CS is 0. Or if A14 is 0, then also CS is 0. Or if A13 is 1, then CS is again 0. So whenever CS is 0, that chip won't be selected, the memory chip. Whenever CS is 1, the memory chip will be selected. So we want A15 to be 1, A14 to be 1, and A13 to be 0 whenever we want to select that chip. There are how many more bits? There are 13 more bits, right? Those can take any value. They can take from 0, 0, 0, 0, 0 to 1, 1, 1, 1. So the lowest value that your entire address bits can take is 110, and then you have zeros everywhere else, right? And then this can go up to 110, 0, and these will go up to 1111. Then the next number will be 111, 1101, 0, 0, 0 to 110, 1, 1, 1, 1, 1. This is the range of address bits that you can have, right? I'm not sure if you are following me or not. Somebody should tell me if that's okay. Okay. So this, what is this number in hexadecimal? You group every 4 bits. So 1100 is A, and the rest are zeros. That will be no. 110 is C. A is 10, B is 11, C is 12. That is 1100. So this is C00 in hexadecimal up to CFFF, and this 1101 is D. D is 13. 1101. So this is D000H to DFFF. Yeah. So C000 to DFFF, but they have split that in 2 parts in the options. So this is the same thing. They have written it in different way. So the number after CFFF is D000. So you could say it goes from C000 to DFFF, but that's also the same as saying it goes from C000 to CFFF and then D000 to DFFF. Okay, so it's option C. If you have any doubts, please stop me and ask. Alright. Next question. The contents of a register B and accumulator A of 8085 microprocessor are 49H and 3AH respectively. So B has the value 49H, A has the value 3AH, The contents of A and the status of carry flag CY and sign flag S after executing sub B instruction are. So whenever only one register is indicated, that means the second operand in this operation is the accumulator. Here A is the accumulator. So when it just says sub B, that means you are subtracting the contents of B from the accumulator. You are doing A minus B. A is 3A. This is in hexadecimal, don't forget. If you forget and make a mistake there, then you will get wrong answers. So this is 49H in hexadecimal. So you have to subtract this. That's the operation. Sub is subtract. Very straightforward. So A is A minus 9. How much is that? It's 1. 3 minus 4. 3 is smaller than 4. So you can't directly subtract 4. So what you have to do is you have to borrow 1 from the next number and carry that to this 3. But in hexadecimal, if you borrow 1, what does it mean? You're actually borrowing 16. So when you borrow 1, that number is 16 plus 3, which is 19. You're subtracting 4 from that, which is 15. 15 is F. Yeah, F1 in hexadecimal. And just from that you can see it's option A, because all the other options have a different content in the accumulator. Suppose two options had the same accumulator content but had different carry and sign bits, then you would need to know how the carry and sign bits are also calculated, right? So for that you have to see that the number A is less than the number B. So your stored number is a negative number, right? So the sign for a negative number, the sign will be set to 1. So S is 1 here. Also the carry bit, this carry flag CY, is set to 1 if there is a carry in an add operation, or if there's a borrow in a subtraction operation. So here we have subtracted and we borrowed 1, right? So this carry bit is set to 1. CY is 1. Okay. All right. Question 6. The clock frequency of an 8085 microprocessor is 5 MHz. If the time required to execute an instruction is 1.6 microseconds, then the number of T states needed for executing the instruction is. So the information they have given us is that the clock frequency is 5 MHz. That means 5 into 10 power of 6 cycles per second. Hertz and cycles per second are the same thing. And then the time required to execute an instruction is 1.6. So it is 1.6 into 10 power minus 6. Micro is 10 power minus 6 seconds per instruction. And what they are asking is the number of T states. That is the number of clock cycles per instruction. So it is 5 into 10 power 6 cycles per second into 1.6 into 10 power minus 6 seconds per instruction. That will give you 8 cycles per instruction. So the answer is 8. Okay. Alright. Question 7. The following 5 instructions were executed on an 8085 microprocessor the content of an accumulator immediately after the execution of the fifth instruction is. So since they're asking us what happens after the fifth instruction, we have to write out what each instruction does. Let's see. MVI A, 65H. MVI is a move. MV is a move operation, that is a data transfer operation. And if they give MVI, that means the data is immediate data. So whatever is given here, 65H, that is the data that you need to move to your register, and the register you have to move it to is A. So A will be equal to 65H after the first instruction. Similarly, MVI B, 12H. So the contents of B will be set to 12H. Add B. So when they give you only one register, like I said in the previous question, it means that implicitly the other register in this add operation. To add operation is a binary operation, right? You need two numbers to add. You can't add one number. Makes no sense. So the other number that you need to add is the contents in the accumulator. Yeah. So you have to add A plus B and store it in A. What is A plus B? 65H plus 12H, that is 77H. And you have to store it in the accumulator, 77H. Next, CMA. What is CMA? CM is complement, and CMA is complement the accumulator. So you have to complement this, but this is in hexadecimal, so it will be easier to complement if you write it out in binary. This is 77, right? In binary, complement is 1000 that's 88, and let's keep it like that. Next instruction is ANI 68H. AN is AND operation. I means that the data is immediately given to you. So 68H is the data with which you have to AND your accumulator contents. So you have to AND 68H. What is that? 0110 1000. You do, and when you do AND, it means you are doing bitwise AND. Okay. So the AND of these numbers will be 08 in hexadecimal. So it's 08H. Is that fine? You need to know these instructions by heart. It's okay for the assignment since you will have the lecture notes, but in the exam they might not give you the instructions, so you will have to know most of the instructions, at least the common instructions like move and add and load. Okay, we'll come back to this question later. I haven't solved it yet. What is the addressing mode used in the following instruction? So in lecture you've seen 4 types of addressing modes. Implied addressing mode, that means in the register which you are dealing with or the data you're dealing with, it's very clear to you which address it is in. For example, CMA, you have to complement the accumulator contents, so you don't need any external address to be given to you, so that is implied. Immediate means that the direct data is given to you directly, so you don't need to get it from some address value, so that's called immediate addressing. Direct addressing, they give you the address directly as a number. So 4000 is the address of the number then you need to load to the accumulator. So in your memory there will be some location called 4000. Hopefully, if you give a wrong number, then it will just give you an error or it won't execute. So if there is a location called 4000 and you say LDA 4000, whatever is stored here will be loaded to the accumulator. That's direct addressing. And indirect addressing, so the address, this 4000 thing will be stored in your register B. For example, in this example, this could have been some other register also, but the address is stored in a register. First you have to read the contents of the register, then you will get the address. Once you get the address, you have to go to that address and read the contents from that address. So it's an indirect way of accessing your data. That's why it's called indirect addressing mode. Here the instruction given is LDAXB, that's an indirect addressing. So the correct answer is option C. Is that clear? Alright, we'll come back to this later. I haven't solved that. This one too. This one also. Okay. Question number 13. What is the size in bits of the program counter in 8085 microprocessor? So we discussed the program counter in one of the earlier questions. The size of the program counter is 16 because the program counter stores an address, and addresses in 8085 are 16-bit numbers. So it needs to have 16 bits. So the answer is option C for question number 13. 14. Which of the following register is not a general purpose register? So general purpose registers are B, C, D, E, H and L, and each of them are of 8 bits. So among the options given, A is not a general purpose register. A is the accumulator. It's a special purpose register. Okay. So question 14, it's option D. Question 15, which of the following flags is not available in an 8085 microprocessor flag register? From the lecture you've seen that there's a sign flag, there's a zero flag, auxiliary carry flag, parity flag and carry flag. So there's no such thing as an overflow flag. So the question is which of the following is not available in 8085, so it's option D. Okay, now we'll go back to these questions that I left out earlier. So I haven't solved these, I'll solve these with you right now. What is the total delay produced by the given program? Assume 8085 operates with 5 MHz clock. Okay, yeah, you guys also try to solve this question. I will take some time to solve it and then we'll come back and discuss. first we need to know what these instructions are, otherwise we can't solve anything. The LXI instruction. Okay, the LXI instruction will load the number that they have given into the register pair BC, and 0123H. So what is this is, the contents of BC will be 0123H. So 01 is loaded into B and 23 is loaded into C. Okay, then there's a loop. DCXB move contents C to A and RA will be JNZ loop. Okay, will they mention time delay in exam? Uh, what exactly do you mean? Venkata? I didn't understand your question. See here they've given you they've given you 10T, 60, 40 and all. Huh. They have they asked a similar question, but they have not given you the delays. Okay. Hmm. Okay. So the I don't know if they'll give you the number of T states. I don't know. Okay, but I don't know what they will do in the exam. They might give, they might not give. Well, for some simple instructions, you can remember directly move and or uh, they'll take only four. But I don't know. There is no proper method to calculate how many cycles it will take, how many T states it will take. So, for example, for the first question in today's assignment, we did it for move AC. how many t states required to execute move AC. So for this you know the timing diagram. So first you have to fetch the instruction here, right? So for fetching it, first you have to load the address of the instruction, and then you have to read. That will take 2 cycles, and then you have to execute, decode and execute, so that will take 1 cycle. So here they're given it as 4 cycles, but in general I don't think there's a good method to find out how many t states it will take. They should give it to you, but I can't guarantee it because I don't set the paper. For common instructions like this J and Z, loop and OR and move, try to remember how many t states will take. In case they don't give it. For your assignment purpose, you can search it on Google now. Usually what is done is all these, the number of t states it will take is specified in the data sheet of the microprocessor. So if you are working with a microprocessor 8085, you will have a data sheet provided by the company that is manufacturing it. So Intel will give you the data sheet, and in that data sheet they will give you the number of t states for all these instructions. Some exam point of view, I'm not sure what you should do. You can try to ask this question in the discussion forum. Maybe the uh, people who set the paper will have an answer. Okay, but anyway, have you solved the question? Have you solved this question? Try it. Whether they'll give you this t-state data or not, that you ask in the group discussion. So those TAs who are involved with the setting of the exam paper, they will check the group discussion and they might answer you. Did anyone solve it? First instruction will take 10 cycles. After first instruction, the number 0, 1, 2, 3 is stored. And then you start a loop. In the loop, what you do every time you decrement B and move the contents of the register C to the accumulator, you OR the contents of A and B, and then you jump J and Z loop. So you jump back into the loop if the Z flag is uh, not set to 0, right? Okay, uh, we'll come back to it later. This will take a bit of time. Okay, we'll do it in the end. We'll do the simpler questions first. Which questions were left out? Question 10 was left. What is the accumulator content of the after the execution of the following instructions? MVI A55H. What will it do? It will move 55H to the accumulator. So A is equal to 55H. What is 55H? It is 0101, right? 0101 in binary. Then you do RLC 3 times. So what is RLC? RLC is this operation. So you have the accumulator of accumulator has 8 bits, and the contents of the accumulator are circulated like this, and then also their last bit is pushed to the carry flag. But we are not really worried about the contents of the carry flag, we are only worried about the contents of the accumulator. So we have to just push the bits to the left cyclically by one place for each of the RLCs. So after the first RLC, what you do is move the entire thing by one bit. So it's 10101011, and this bit is shifted to the end. So it's 0. The next RLC, what you do, again move it by one bit to the left. R is rotate and L is rotate left, so L is left. That's how I remember it. That's probably how they named it also. Okay, and 0101 this one gets to the end. One more RLC, 1010 this bit comes to the end. So what happened in the end? You have 1010 is A, this is also A, so it's A in hexadecimal. The correct answer was supposed to be B. Alright, we got B, so it's correct. Any doubts? So MVI move immediate data means that the immediate data, whatever number that is given, is moved into the contents of the register. It can be other registers also. And then once you have moved 55H to the accumulator, RLC, what does it do? It shifts the bits in the accumulator one place to the left, and the final bit is pushed into the carry flag and also to the first bit in your register. And here they have done this RLC operation thrice, so you have to do this 3 times and you get AAH. Is that okay? You should tell me if it's okay or not. You can. Alright, I'll just move on. What are the contents of BC register pair after the following instruction is executed? LXI B ABCDH. So again, whenever you see I, that means the data is immediate. So this data is directly given to you. ABCDH is the data. And LX, what is that operation? It is LXI. It's a load operation, right? Let's see. LXI is load extended immediate. So it will place the number that is given ABCDH into the register pair BC. So instead of saying BC, you just say B, and it is automatically understood that the register pair is BC. Similarly, if you say H, it is automatically understood that the register pair is HL. Same for D also. If you say D, then D is your register pair. So ABCDH is loaded onto the register pair BC. So B will have AB and C will have CD in hexadecimal. That's option C. Okay. You just need to know how the LXI instruction works. When you see L, usually it's a load instruction, and when you see I, that means the data is immediately given, and when you see X, it usually means that you are working with register pairs. So BC in this case. Okay. Question number 12. So we have to do 12 and 8. Question 12. What is the content of the accumulator after the execution of the program? Assume 8085 flag register is initially reset. That means all your flag bits are 0. Okay. MVI A, F2H. So your accumulator is F2 in hexadecimal, because MVI will move the immediate data to F2H to the accumulator A. RRC, we saw RLC. For RRC, it's the same thing except that the bits are shifted right instead of left. So F is 1111, 2 is 0010, and you have carry, it was reset to 0, you're shifting things right, and it's an RRC operation, so you're shifting this way. Okay, so the carry bit is still 0, but the number is 0 1 1 1 1 0 0 1. So now A is 7 and 9H. Okay, move AB. So the accumulator contents are moved to register B, but a move operation doesn't change the contents of the original source. So the accumulator content is still this, and B is also 79H now. Okay, RAL, RAL. So different from RLC or RRC, RAL, the carry is considered part of the number. So you would have to, for the first RAL, you would move this bit to the carry, the final bit. Carry bit would be moved to the first bit. So the number will become 1111 001 0 with carry 0, and you do that again. This is one RLC, not RLC, it's RAL. Next, one RAL. Once more you do RAL. What will you get? You will get 1111 0 1 0 0. Carry will be 1. So your accumulator has become, what is 1110? It is, in hexadecimal, it is E, right? E, and 0100 is 4. E4H. Then you add B. So that is, add the contents of register B to the accumulator and store it in the accumulator. So E will become, accumulator will become E4H plus 79H. What's this? 9 plus 4 is 13. 13 is, A is 10, B is 11, C is 12, D is 13. So it's D. E plus 7 is, what is it? E is 14 plus 7. So 1, 1 plus 1 is 0 with a 1 carried over. 1 plus 1 plus 1 is 1 with a 1 carried over. 1 plus 1 is 0 with a 1 carried over. So you get 0101, which is 5D H, and there was a carryover. So carry bit is still 1. And then you have to do RAR. So you have 1 in the carry, you have 0101, you have D, which is 13. You have to do rotate right. So shift it right with your carry as an extended bit. So it is 1 0 1 0 and 1 1 1 0. Your carry will be 1. So this is your accumulator content now. 1 0 1 0 1 1 1 0, which is in hexadecimal. What is it? It's A. This one is what? E. AH. So the correct answer was A. It's AH, right? So this is correct. Any doubts? You just need to know the operations and you need to perform them properly without making any mistakes. So if you make a mistake when shifting these bits, instead of writing 0, you write 1 somewhere, you will get the wrong answer. Or if you forget a step. So we actually got 5DH here, 5DH. So if you forgot to do RAR, you would have the answer as option C, which is wrong. So the options will be set such that you'll make mistakes. So you have to be a bit more careful. Is that okay? Alright. So we'll solve this question now. This is the only question left. So at least I'll explain what is happening and then we'll do the actual computation. First LXI B, 0123H. It's loading onto the register pair BC the number 0123H. B will have the first two numbers 01 in hexadecimal and C will have 2 3. So since in hexadecimal each of these is 4 bits, so this is 4, this is 4, so one byte is stored by B and the other byte is stored by C, and this happens once, so this takes 10 clock cycles, so you have 10T, and then there's a loop. Inside the loop, what is happening? DCX B. So when I told previously in one of the other questions that whenever you have X, that means you're doing an extended operation. That is, you're considering the register pair BC as one unit and you are decrementing the register pair instead of decrementing only the register B. So 0123 is actually 0000, 0001, 0010, 0011. This is decremented by 1 when you do DCXB. So it will become 0000, 0001, 0010, 0010. And then move A, C, it will move the contents of C to register A. So here, this is the contents of B, this is the contents of C. Now once you are done DCXB, the contents of C are 0010, 0010 and 0010. That is 22H. This is still 01H. So your A will become 22H. Then you are ORing that with B. ORA is OR only, right? ORA or accumulator with the register or memory. So here ORAB means OR the accumulator contents with the contents of register B and store it in the accumulator. So accumulator has 22H, B is 0 H. You have to OR these two, store it in OR of A and B, store it in the accumulator. So what is the OR of these things? 0010 0010 ORed with 0000 and the OR is carried out bitwise. So 0 or 1 is 1, 1 or 0 is 1. 0 or 0 is just 0. So you get A is equal to 23H. And then you have J and Z loop. J and Z is a jump operation. It's a conditional jump operation. So if the 0 flag is not set, so that means if the 0 flag is equal to 0, then it will jump to the previous initial position again. So it will jump back here if Z is not equal to 0. And so we need to keep track of the Z flag. DCX, move AC, or A comma or AB, all these you have to check which of these will change the contents of the Z flag. Let's see which of them does it. So the 0 flag is set if result obtained after an operation is 0, or is set following an increment or decrement operation of that register. So after you perform an operation, if the result is 0, then the 0 flag will be set. So until that 0 flag is set, this loop will go on. The loop DCXB, move AC or AB. So we have to count how many times those instructions happen. Let's say they happen n times. Okay. So the total number of t states will then be, for initially 10 t states occurred, 10t plus n times. So this statement takes 60 states, this takes 40, this takes 40, this takes 10t. So this total thing, it will take 24t. So if this happens n times, then the number of cycles will be this much. It will be 10 plus 24n cycles. Okay, and then they're given that the 8085 operates with 5 megahertz clock, that is 5 into 10 power 6 cycles per second. So the total delay will be equal to 5 into 10 power 6 10 plus 24n divided by 5 into 10 power 6 seconds. So our goal now is to find out how many times this loop occurs. This loop will keep occurring until the Z flag is set to 0. Let me see. So this move operation doesn't change your zero flag, so you don't have to worry about that. We only have to worry about DCX and ORAB. Uh, Give me 5 minutes, guys. Or you do one thing. I will work this out and post it in that group that they've given, right? Where I will post these slides. I'll work it out and post it. Or if you stay for 5 minutes, I will try to tell you the answer. Or else you can leave and then I'll work it out and post that in the group. Okay. Any objections? Is that fine, Bharti and Mukesh? Okay. Because I haven't solved this question, so it will take some time. Uh, but you understood the method to do it, right? You have to calculate how many times this loop occurs, and then the first instruction LXI takes 10 cycles, so the total number of cycles will be 10 plus, and each of these loops takes 24 cycles, 6 plus 4 plus 4 plus 10. So the total number of cycles will be 10 plus 24n, and you take 5 into 10 power 6 cycles in 1 second. So the time taken will be the number of cycles divided by the number of cycles per second. So it's 10 plus 24n divided by 5 into 10 power 6. So that's the method to do it, but finding out exactly how many times this occurs is you try it out yourself. I'll do that and post the solution later. Okay, all right. Yeah, recordings are all posted in the YouTube channel. So okay, actually, you're there on the NPTEL website, NPTEL course, right? You have joined that course. Are you there in the course? One minute. I'll stop recording. Then I'll answer your question.